So in the last video, we talked about de Broglie's equation or de Broglie relation. Lambda is h over mv, and we said velocity is related to the wave nature and position is related to particle nature. Okay, particle has a position, wave doesn't have a position. So if electron behaves like both wave and a particle, we won't be really able to measure position and velocity at the same time. This is given to us by a principle known as Heisenberg's uncertainty principle. Delta x multiplied by m delta v is greater than or equal to h over 4 pi. H over 4 pi. This is known as Heisenberg's uncertainty principle, named after the scientist Heisenberg's uncertainty principle. If you think about it, first of all, delta x is uncertainty in position and delta v is uncertainty in velocity. If you think about it, the product of these two numbers, as in this multiplied by this, should be equal to a finite number. Now let's say uncertainty in position is very, very small. So let's say we know the position accurately. Position we know very accurately. That means uncertainty in position is very less. So delta x is small. In that case, delta v becomes large because the product should be equal to a finite number. On the other hand, if we know the velocity very accurately, that means there's no uncertainty or very little uncertainty in velocity. That means delta v is small. And since the product is equal to a finite number, delta x becomes large. Try it with some known numbers, like use delta x is 0.01 or something, and you will see the numbers. So this is known as Heisenberg's uncertainty principle. And what does it state? It states that, or it tells us that you cannot simultaneously measure or you cannot locate an electron at the same time measure its velocity. So you can only notice either the wave nature or particle nature at a certain point of time. If wave nature is dominating, then particle nature does not dominate. But in some cases, when particle nature dominates, wave nature is very, very suppressed.